Oh, I don't know. Okay, today we are doing the quotient rule. Quotient rule of derivatives. All right, so far, as far as our rules of derivatives, just to make sure that we are remembering them, if we take the derivative of sine, that gives us a cosine. And if I take the derivative of cosine, I get a negative sine. Good. And if I take the derivative of tangent,
secant squared.
yes, secant squared. And if I take the derivative of, and this will be our, did we get this one yesterday? The derivative of an exponential gives us the natural log of that exponential times the exponential. So we'll actually be using that one today. And then, just to throw in one other one, this is also on the board. If I have the log base, I want to write it the same as on the board, base A of x, okay, that is going to be 1 over natural log of A times x, okay? So these are, so far, are just memorize these. Memorize. And then we have our chain rule, which we're going to use a slightly different notation for, just because it, well, maybe I can do it with so if I have a h of x equals f of g of x, then the derivative of that is going to be f prime of x times g prime of x. Or using the other notation, dy dx equals dy du times du dx. And then we have the product rule, which we'll just go ahead and use this notation for. If I have some function that I could write as f of x, g of x, then if I want the derivative of that, so if I have h of x equals some product of two different things, then the derivative of that is going to be f prime of x, g of x, plus f of x, g prime of x. And that is our product rule. Okay, today's rule, so this is everything that we've done, plus we have these two new, like, memorize those. Today is the quotient rule, which is going to be very similar to the product rule. Is if I have some function h of x, and I can write it as basically a fraction, then the derivative of that is going to be f prime of x, g of x. So it starts out like the product rule, except instead of adding these, I'm going to subtract them. F of x, g prime of x. So far same as product rule, except I subtract these instead of add them. All over, and now another difference, I take g of x and I square it, whatever it happens to be. Alright, so an example of this. So let's say I have 3x squared all over 4x to the third plus 2x. And that's my function, y equals that. So I would say my top is basically my f of x, and the bottom is my g of x. So the whole top, the whole bottom. So if I want the derivative of this, so dy dx, that's the derivative, and just understand what this means. This means the derivative of function y with respect to the variable x. That's what that means. Okay, so rate of change. So I'm going to do this quotient rule because I have a top part and a bottom part. So the derivative of f of x, the derivative of the top is 6x, and the derivative of the bottom part, So I take the derivative of that is 12x squared plus 2. Now I just plug those, each part, into this little formula. So f prime of x is 6x times g of x minus, now I do f of x times g prime of x, and then I square my denominator. So I have 4x cubed plus 2x, and I square. We can go ahead and simplify as much as possible. So I have 24x to the 4th plus 12x squared minus 36x to the 4th minus 6x squared all over, and I'll go ahead and expand this, 16x to the 6th plus, let's see, we'll get an 8, but we'll have 2 of those, so 8x plus 8x, that's going to be 16x to the 4th plus 4x squared. Expanding that, multiplying it out. Combine like terms. So 24x to the 4th. Oh, nope. I have a 36 there. So negative. Looks like 12x to the 4th plus 6x squared all over this. Looks like I can divide it all by 2, so I will. So divide it all by 2. I'll put my answer at the top right here, just because. So negative 6x to the... Oh, and I can divide by an x squared. So negative 6x squared plus 2 divided by... Nope, that's going to be a 3. Because 6 divided 2 is 3. Divide that by 2 in an x squared, so 8x to the 4th plus 8x squared plus 2. And that's as far as I can reduce that. That's my derivative. That's dy dx. That's my derivative. Okay, yesterday in class we ended with a square root, and we were kind of having trouble figuring that out. And the key to any square root or any root is to recognize that you can write it as an exponent. So if I have y equals root x, you really need to rewrite it like this. And it's going to work the same way as this one. So if I have x squared, what's the derivative of that? What's the derivative of this? 2x. I decrease I take whatever this is, my exponent, multiply it by my coefficient, so 2 times 1 is 2, and then I decrease it by a power of 1. That's the whole idea of that rule, or the power rule. So if I have y equals ax to some exponent, the derivative of that is going to be a times n times x to the n minus 1. That rule applies to this. A radical is simply a fractional exponent. So I can take the derivative of that. A half times 1 is a half x, and then I decrease this by 1, but 1 half minus 1 is a half minus 2 over 2, which is negative a half. And then we're going to rewrite this back into radical form. So I put that into my denominator, and I get 2 root x. Like this. That's my dy dx. Okay? So we need to be, even though we might have fractional things, we need to be solid on doing them. So let's apply the quotient rule. Let's say my y is root boy, yeah, let's do a really hard one. Here we go. That's not going to be that bad, but it'll still be challenging. I am going to have to use two rules in this, and that will happen often. My two rules that I'm going to have to use, I see I have a function at top, Samantha, and I have a function at bottom. I need to find a quotient rule. I also have within this a function within a function, so I have a chain rule. So I have a chain rule and a quotient rule that I'm going to have to use. So if I'm finding the derivative of this, it's going to be my quotient rule. So f prime of x, g of x, minus f of x, g prime of x, all over gx squared. So what is f of x? Well, f of x is going to be the top. So that's root 3x minus 5. Well, now I need to take the derivative of that. Well, to take the derivative of that, I need to do a chain rule. So I'd say y, in this case, equals root u, and u is the 3x minus 5 from yesterday. Then that means du dx equals the derivative of this, which is 3, and then I do the derivative of that, dy du, the derivative of function y with respect to u. This is the derivative of function u with respect to x. That's going to be u 1/2. Well, I'm actually not there yet, so I should say this is y still. So now dy du, now I'm going to take the derivative, a half u to the negative half, just like over here. Then I move that down, so 1 over 2 u to the half, write it as a radical, so 2 root u. Then apply the chain rule. Dy dx equals dy du times du dx. So that's this times this. What's the denominator on this?
1.
A 1. So I have 3 over 2 root, well, what's u? U is 3x minus 5. Okay, so the derivative here of f of x is 3 halves, and in my denominator, 3x minus 5. Okay, now I'm going to erase all this because we need some room. Now I need to find the derivative of g of x. Well, g of x is my denominator. It's 4x. The derivative of that is 4. Okay, so continuing this down here, dy dx equals f prime times g prime. So this, or f prime times g. So these two multiply. What's my denominator on this one? 1. So it's 4x times 3. So that's going to be what? 12x.
Got washed.
Great. So 12x all over. Well, this 2 will cancel with that 12, right? Or that 4. You see what I'm saying? That 2 cancels with that 4, so I actually get 6x all over root 3x minus 1, or 5. That's this piece. Then minus f of x times g prime of x. That's 4 root 3x minus 5. These two multiply. all over. I square my denominator. That's 16x squared. That's my derivative unsimplified. You get where that comes from. For the sake of time, we'll say we'll just leave that, but technically what we'd want to do is get a common denominator here. If we were to get a common denominator, just working on my numerator, this fraction is missing this denominator, so 3x minus 5, common denominator. I multiply that, so I get 4 times 3x minus 5, because top times this root 3x minus 5. And then I could distribute that 4, so I get 6x minus 12x plus 20. So negative 6x plus 20, all over root 3x minus 5. Well, since I started it, I might as well finish it. So that's my numerator combining that. All over 16x squared. Keep, flip, change, right? To go ahead and get this flip, so 16x squared over 1. Now the x's don't cancel, but I could cancel 2. So I get negative 3x plus 10 all over 8x squared root 3x minus 5. And then we could rationalize, but I'm okay at this point if we just go ahead and say we'll just leave that. Okay, so that's good. That's this simplified. And we really should get it a little bit better than this. This is pretty messy, right? Got a common denominator, combine. There are a lot of little steps. Do you notice what we learned about fractions applies? Okay? What we've learned about rationalizing applies. One more example. Let's say y equals tan of 3x plus 2. We'll do 3x squared just because. All over, let's say, 5 to the 2x plus 1. This is a quotient rule. Do you see? A top and a bottom. A chain rule right here, and a chain rule right here. So there are a lot of steps. We start by writing down our quotient rule.
I'm confused. Why wouldn't it be a power rule in the denominator?
Huh?
Why wouldn't it be a power rule in the denominator?
A power rule would apply for something like this. But that's not what I have. I have this, or something like it. Okay? That goes back to, I told you today, we had this one that we were going to use today. So this is a new derivative. You need to memorize it. Any exponential, which is when our number is the base and our variable is the exponent. Okay? G of x minus f of x, g prime of x, all over gx squared. Now I'm going to be flipping to different slides because this will take up a lot of room. And it should, because there's a lot of different pieces here. So I'm going to just say f of x is going to be my numerator, right? And my denominator is g of x, which is this 5, 2x plus 1. Now I'm going to take the derivative of f of x. I'm going to take the derivative of g of x. If you organize your work, you'll be a lot more successful. Okay, so now somewhere else I'm going to go ahead and do this derivative, tan of 3x squared plus 2. Right, just double check to make sure I got that. Yep. All right, so this is a chain rule. What is u?
3x squared plus 2.
Okay, so y equals tan u. All right, what's dy du? Secant squared u. And what's dy or du dx? 6x. Okay, that means dy dx, the derivative of this with respect to x, is 6x times secant squared, and then I replace the u with 3x squared plus 2. That is my derivative for this. Okay, so I'll go back here, I'll just write that down. 6x secant squared of 3x squared plus 2. Is that what we had? Yes. Okay, now I need the derivative of this. 5 to the 2x plus 1. So y equals 5 to the 2x plus 1. What's u?
Would be 2x plus 1.
Yep, 2x plus 1. I take the derivative of u with respect to x. Pretty simple, it is just 2. Then y is 5 to the u, and the derivative of y with respect to u is natural log 5 times 5u. Right? This rule. Right there. Okay? So we did that derivative. That means dy dx equals 2 natural log 5 times 5 to the 2x plus 1. I just multiply those two. Now I take this, I'm going to move it to natural log 5. Times 5 to the 2x plus 1. Okay, now at this point we are ready to go ahead and do our quotient rule. Notice I had to apply some chain rules before I could go right to this. So f prime of x, I'm just going to plug them in. 6x secant squared 3x squared plus 2 times g of x. Now I want to be very careful here. That I make it clear that this 3x squared plus 2 is the argument of secant squared, and gx is being multiplied by it, or not by this. So it really looks like a mess here. It is a mess. Okay, I'm going to put those down here so they're out of the way, because this is going to get really large. What was our f prime of x? Just making some room. G prime of x equals okay, now I have room. Okay, minus f of x times g prime of x and then over g squared. So that's going to be 5 to the 4x plus 2. Why? Because of power to a power. What do I do? Power to a power. What do I do with the exponents? Multiply them. So that's where that comes from. So that is the final answer, dy dx. Lots of little steps. But we are happy. Why are we happy? because we did not have to try to do this by taking a limit as h approaches 0, f of x plus h minus f of x all over h. We are very happy we did not have to try to do that. Even though this takes a lot of space, it is by and large better than trying to do this. Okay.